As we got a few people coming in, we'll go ahead and get ready here. So this morning we're going to look at LiDAR systems, data collection, processing, patch testing with the LiDARs. How many people here have LiDARs currently? Okay, about half the room. What's the great thing about the LiDAR systems that are out on the market today? Initially, the first ones that came out were uber expensive. The Optec Ilris, several of the Regal systems, the Dynascans that came out, you know, they were $50,000 to $150,000 just for the piece of equipment. With the onslaught of the car industry wanting to do autonomous driving, they're implementing the lasers to do that by. And several years ago, there's a contest out in the desert where you use some form of fashion to navigate a desert course completely autonomously for the car, and no one had ever made it until Vegetation developed this 360-degree spinning laser with 16 channels. They put it on the car. It was the first car ever to complete the course, and they progressed from there, and the cost of the lasers has gone down considerably, and now there's more and more popping out. I saw one the other day that's like $500. It has like a 40-degree swath, and but you know, depending on what you're needing to survey with it, we don't currently have a driver for that one yet, but if we did, then you could certainly use it. But the systems that are on the market now, the Vegetation that I'm getting ready to hook up and show you just how simple they hook up and work, are in the $5,000 range. And you know, since we're pretty much all hydrographers here, how many pieces of equipment do you have on your vessel right now that cost less than $5,000? The coffee pot, okay. The microwave, potentially, I don't even think the sound velocity profilers are that cheap anymore. But anyway, the one thing about, a couple things to be aware of if you're going to do LiDAR surveys is they do require all the pieces of equipment that a multi-beam sonar system would require. We need position, we need motion, we need heading, and most important of all, they require RTK either post-processed or in real time, because the lasers are much finer points than what a multi-beam system would be, you know, because you know, even the finest multi-beam system is going to be like a 0.3 by 0.6 beam spread. In LiDAR systems, they call it beam divergence. So if I get my handy little laser pointer out here, this little red dot on the wall is what everybody thinks of a laser, okay? Well, lasers still have what they call beam divergence, which means they do spread. That light beam does spread as it goes out. It doesn't stay this fine little point. So depending on the laser that you buy will depend on how accurate or how small their beam divergence is. So the Vegetation that I'm going to hook up has a 3 millirad beam divergence. So I had to look up how small millirad was, and the number 3 sounded pretty small to me as well. So when you do the convergence to degrees, 3 millirads is equal to 0.17 degrees, roughly. All right, so the Vegetions have a 100-meter range. That's another reason why they're an inexpensive piece of equipment. So, but 100 meters is basically 330 feet, right? But at 330 feet away, this red dot is 12 inches in diameter. So it has a larger footprint. So the further it gets away, the resolution that it has on the objects that it's striking are a little bit fuzzier than a nice crisp 90-degree corner like we see around here. They also have the ability to do what they call first return or strongest return and last return. So if I have this 1 foot diameter light ray going out and it strikes this microphone right here, it can continue on and strike that back wall. So this would be my first return, that would be my last return. It will actually do dual returns, right? So, but it's going to also double how many data points it collects. So this laser that I'm going to hook up can collect 300,000 points per second. So better have a solid state drive, better have a computer that can handle the data coming in, i5, i7, quad cores, lots of RAM to be able to store all this in real time. So again, RTK is one of the key things that we're going to have, whether it's done in real time or whether it's done post-processing through programs like Hypack or Inertia or the programs that Coda has and the other inertial systems. So I'm going to hook up real simple to show you what this requires, and I've done demonstrations all across the country and around the world with this system. And I can literally get on your boat and within about 10 minutes have this set up, ready to collect and do a demonstration for you. So I'll just show you what it looks like here. So if you're familiar with the McDonald's Big Mac, it's about how big it is, right? $5,000 or less, depending on what their cost is now. But it's got a simple cable that's typically hardwired. I cut mine to a nice little interface box here. And basically the interface box has 3 connections: your network connection, a power connection, and a GPS connection. And the reason for the GPS connection is purely to get timing, right? So Velodyne was real simple, and they found this nice little Garmin GPS that has this nice little micro 1.0 JST connector, which took me 3 orders from China to figure out what size it was. And it plugs right in here, and the only purpose it serves is to give the timing to the laser. It doesn't matter where you put this antenna on the boat. We're not using it for the positioning. It's purely to get the timing to the laser, so that when the laser data comes into the computer, it's all time synced to UTC. All right? So quick connection here. It requires 12 volts, and if you want, you can find all kinds of these nice little lithium-ion battery packs like this. They'll run anywhere from, I actually just bought another one for about 60 bucks. But they'll run from 60 to 160. This battery right here, according to the manual, will jumpstart a diesel truck. It actually does come with a set of alligator clips that plugs in right here and supposedly will jumpstart your car. So I've not tried it, but I don't believe it. So just hook up to the 12-volt connection here, plug in the power. 2 little green lights come on the Velodyne. The same type of thing would happen on the topside unit of any laser system. I'm going to plug in my network connection. I've also got this nice little portable mount that I had built. And this comes courtesy of a design developed by the New York Corps, who figured out that if we do a 45-degree tilt, there's a specific reason for doing this, and I'll explain that in just a second. But, so the Velodyne's real simple. It just has a simple 1/4-20 bolt that screws right in the bottom of it to hold it on. The plate here has 2 little pins that come up, and these are guide pins that match up to the guide holes on the bottom of the Velodyne here, so that you can leave the mounting bracket on your vessel, truck, whatever, all the time. Take the laser off just for security, because you don't want to drive down the road 75 miles an hour and hopefully a tree branch or something doesn't take this off. So if you got the guide pins, you can just set it on. Always goes back in the same location, same orientation, so you typically don't have to patch test every time. screw your quarter 20 bolt in, it's ready to go. You've got this already patch tested, it's inside your hardware, and we're going to walk through that in just a second. And it's spinning, it's ready to collect data. Again, it connects by a single Ethernet cable. So typically you would have something on your boat, you know, if you've got multiple devices that connect through a network, like a POS-MV, maybe you've got an ODM single beam that does network port, a Knudsen, your multi-beams connecting through a network port. So typically most computers don't have multiple network connections. They simply have one. So getting something like a network switch like this, where everything plugs in and then this plugs into the port on your computer, that'll bring all the data in at one time. So the first thing that we need to do is make sure that we can get the IP address talking to the laser here. So in order to do that, we're going to go to our control panel in your computer. We're going to go to the Network and Sharing Center. We're going to change our adapter settings. We're going to right-click on our local area connection, go to Properties. We're going to go to the IPv4 connection, click on Properties, and we want to set a static IP. All right? So to talk to this laser, it's 192.168.177, and this is in the manual, so make sure you read the manual. Hit the tab button, it automatically sets the subnet mask for you, and click OK. Close it. So now my network connection is ready to talk to this. If all works well, I should be able to come down here and open up my internet browser and type in the IP address of the laser. And again, that's going to be a simple 192.168.1.201. And there's the controller for the laser. So you can see that the laser's turned on. It's currently set to the strongest return. I could set it to the last return. I could set it to dual return. All right. Typically, most people leave it on strongest, but one of the things that a lot of people are doing with the lasers is bank line surveys. They're doing all kinds of land terrestrial surveys with them now. But the one thing that they're looking to do is get to, we'll just call it simply bare earth. All right? So if you've got vegetation and you're trying to get to bare earth, then dependent upon how thick the vegetation is, will determine whether you see bare earth. They do not penetrate through vegetation, trees, leaves, tall grass, whatever. The light ray has to find its way to the ground and return. Right? So if that doesn't happen, you will never get to bare earth. So just be aware that that could be a potential issue. And I'll explain that a little bit more between the way this one works versus some of the other lasers. And I'll just touch on that right now. So a lot of the other lasers just have a single 360-degree rotating laser. Some of them only have like an 80-degree opening. All right, and it's a single laser that's going out. Well, if that single laser as it's passing by never hits the ground, then you'll never see it because the vegetation blocked it. Now, a system like the Velodyne has 16 channels. They're going out in a 2-degree spread across the channels. 15 degrees to one side, 15 degrees the other, so I've got a 30-degree swath and 16 beams across it. Now, if I'm scanning a bank line, because I've got these 16 channels that are kind of on different angles, it's very possible that they'll get through the vegetation and see the ground and get a return. All right? So with a system like this, it may have a better chance of getting through vegetation to get to the real earth and get back. So that would be an advantage of a multi-channel laser like this versus a single channel laser like the Merlins and the Optex and the Regals. So that's just something to look at that this system could offer that another one couldn't. You can also change how fast the laser spins. All right? So the faster the laser spins, the more data you're going to get, except, remember, this laser's spinning in a 360-degree circle, so what they call the angular resolution changes. The slower you spin it, the better your angular resolution is, meaning if there's a smear across an object. So if you've got some kind of a vertical object, the slower I spin it, I'll have a 1/10 of a degree resolution. If I double that speed, it's a 2/10 resolution, which means it's smearing a little bit along this object, so it's not going to be as crisp. If I go to the fastest speed on this, which is 1200 RPMs, then it's a 4/10 resolution. All right, so 300 is the slowest for this particular system, 600, 1200. You can set it anywhere you want. It's just the angular resolution changes, which means the crispness of objects is going to change as it strikes it. So typically, most people leave this at the 600, which is the 2/10 resolution. The FOV, that's the field of view. So remember, it's spinning 360 degrees. So I can trim down what I want it to look at. If I'm only looking at this side of a bank line, I could say only give me data coming in from 30 degrees, or let's say 60 degrees from straight up down to 120 degrees. I could just open up a small fan. We typically recommend that for the controller of the LiDAR itself, leave it wide open. In Hypack, during survey, we have the ability to squeeze that down. So we would just prefer that you have the LiDAR system, just send us everything and let us trim it down in the survey program. That way, if somebody gets in here and set this from 0 to 2 by accident, it's only going to have a little 2-degree window that it opens up and you may never get anything. So leave it wide open. The other thing that's critical about the Velodyne is right down here where it says GPS position and PPS. Again, that's where this little GPS comes into play. When you plug this in, it's sending an RMC message. That's what they use to do the timing by. So it sends the RMC message from this GPS, and it'll show you a valid latitude, longitude down here in the GPS position, and also in the PPS box, it will say locked. All right? If you do not see locked in that PPS position, I would not survey because all the timing is going to be bad for all the data that it's sending in. All right? So this is a critical step to have this piece of equipment. You do not have to have this. But if you don't, then you need to be able to order one of these micro 1.0 JST connectors and wire it into your GPS so that it's outputting and sending the PPS and the position timing data through the RMC string. All right, so again, this is just the controller. Once this is set up, you don't have to have it up anymore. We can simply close the browser, or a lot of people just minimize it in case they want to go in and slow down or speed up the RPMs on it. So it doesn't hurt to have it there. So we'll go ahead and open up Hypack. It's real simple to set up. It's no different than adding another device in the software. All right. So I'm just going to do a nice simple little project. Typically we recommend that if you start a brand new project that you go to the Halifax project. The Halifax project has been in Hypack since 1999. It's what we consider our bulletproof project. It contains no inherent issues that we have ever been aware of. So if you start from it, we know that you're going to have a nice clean project to start from. So I'm just going to simply come up here, File, New Project, and we'll just call this LiDAR Demo. All right, I'm not really worried about the geodesy in this room, so I'm just going to leave it to the default that the Halifax project had. I'm going to go to the hardware. I'm going to do File and New just to wipe everything clean. And I'm just going to set up 2 simple devices under the boat. I'm going to use our Sim32, which is just a nice simulation driver for positioning. I'll set it up and say that its initial position is at 50,000 with an initial heading of 0. Say OK. I'm going to go to hardware, tell it to include high sweep. I'm going to currently remove the playback. I'll just disable it. And I'm going to add the Velodyne. All right. We have 4 different Velodynes, the HDL32E in either a horizontal or vertical mode, or the VLP16, again, in the horizontal or vertical mode. So I'm going to put it in the horizontal mode, which means it would be laying flat like this. In the vertical mode, it would be at 90 degrees like this. So we're going to set it at 45 degrees, and as soon as I set it up, I'll explain why. So I'm going to add the horizontal. First thing I'm going to do is just go to the offsets and tell it that it is pitched 45 degrees up from horizontal. So that's now set up to the orientation that it's in right now. We'll go to connection, and somebody's phone went off. I want to make sure mine doesn't go off. We'll go to connection, and again, just about any network device that Hypack has a driver for, we currently already put in the default port number and the default IP address to use. So that's already set up here, so I'm good to go. And if I wanted, I could go to the network test, I could ping the device, it sees it, and UDP connect, and I can see that the data is coming in. So I know I'm talking to it, I know the data is coming into the driver, so I'm good to go here in hardware. So I'll just simply close this out, save it, and I'm good to go. All right, so the reason for the 45-degree tilt is if I had just a simple single channel laser that's just spinning like this, and if it's in the vertical mode, as the boat or vessel is moving along, it's just scanning straight out from the side of the boat, okay? If this was some type of tall cylindrical object that I'm trying to pick up, like a light standard or a tree, okay, then it's very possible that as the LiDAR goes by here, I might miss this object just depending on how fast it's spinning. But now if I turn my LiDAR on a 45-degree angle, if anybody's familiar with the old barber poles that had the red, white, and blue stripes, right? They're on a 45. So imagine that if I'm going by this tall cylindrical object, if my LiDAR is spinning on a 45 degree like this, then I'm going to catch it at the very top and I'm going to candy stripe it all the way down. So I will see the full semicircle from this side of this object, and it will get picked up in my LiDAR data. Where in a vertical mode, I potentially could pick it up, but I might only get 1 or 2 stripes on it. And I'll see that in the editor and try to figure out what is this thing that's got 2 stripes on it, or 1 stripe, right? And I may not catch the full tangent edge of this, so I don't get the full size of it. But with the 45-degree tilt, I candy stripe this all the way down to the bottom, and I know exactly what this is. So that's the advantage of doing the 45-degree tilt, and I applaud the gentleman from the New York district that designed this and have let me display this around the world. All right, so with that said, everything's up and running. I can just simply start the survey program and tell it that I'm doing the Velodyne. I don't need the waterfall though. I want the real-time cloud window. And let's just expand this full screen. Change my boat settings to something like 0.5 width, 5.5 length, 5.5 height. All right. So here we are. So there's the laser right now, spinning 360 degrees circle, scanning with all 16 lasers running right now. And we can see the 45-degree tilt. And you can see how the back wall has the beams spread apart. Oh, well, hold on a second, Katie. So let's see. Katie, you're probably not in the field of view, but let me twist it just a little bit more. And give me a second. I got to clear this out. So you're going to be, so just kind of, up there you are, you're right here. So remember, when this is spinning 360 degrees, it's collecting up to 300,000 points per second. The fastest multi-beam, even if it was at 512 beams pinging 60 times a second, is 30,000 points per second. So this potentially is collecting 10 times the amount of data points that the fastest multi-beam would be collecting. And the fastest multi-beam to be pinging at 60 hertz would have to be in about a meter or two of water. All right? So this is reaching out 100 meters and collecting 300,000 points per second. So again, one of the things that we recommend with the multi-channel lasers like this is that you don't need that kind of data. Believe me, and you can ask any of the guys, the New York cores here, New Orleans districts here, Philadelphia, they're also here. They've got these Velodyne lasers. Typically, what we recommend that you do is turn on the inner 2, inner 4, at most the inner 6 of the 16 beams. All right. Under the control, the high sweep controller, under the tools, we have the Velodyne controller. And this is where I can turn on or off however many beams I need. All right. So right now, all 16 channels are turned on. I have the ability to set a range filter, which this becomes really handy if I've got this mounted on the top of a boat. I don't need to be scanning the boat on every single ping. All right. So I could set this to, something like, and I'm in a meters project right now, so anything I set in here distance-wise will be meter related. So I could set this to say 3 meter minimum. I could hit apply, and now you can see that it has cut out the first 3 meters of what it's collecting. It will not be in the HSX file. So what you're doing here is affecting the data points that we're collecting. And as a max, if I knew that I get my best data out to 75 meters from the laser, then I might want to set a max value at 75 meters and have it clip there as well. All right. These are things that you're going to learn about the system when you have it. And Miguel, when you guys use it, is there a max distance that you all like to use? 50 meters, okay? At 50 meters, you're still talking about 165 feet away from the boat. All right. Typically, you're looking at surveying jetties and bank lines and aids to navigation. So if you're doing anything where you're doing ENC work or INC work, and you have to map the underclearance of bridges and bridge locations and docks and buoys and anything like that, where typically before you had to pull up beside something, take a target in Hypack, so you had to come to a full stop, take the target, then run it over to the next object, take a target. Well, imagine having this set to like 6 channels, and you're going down the body of water at 20 miles an hour and collecting everything you need with very accurate positioning and heights. So now when you get into the editor, you can do all your targeting in the editor and go, oh, there's the green buoy, there's the red buoy, there's this aid to navigation, oh, here's the bridge pier. Now you can do front and back points of the bridge pier. You can do corners of lock walls. You can now know what the underclearance bridges are that you can put in your charts and maps. And you can collect all this at speed. And again, we're talking about a piece of equipment that's $5,000. All right? And if you already have all the other peripheral equipment, again, position, motion, heading, RTK, that you'd be using for your multi-beam, this is no different than just adding a simple piece of equipment to your hardware. All right, so again, talked about you don't need all 16 lasers, and I promise you that if you do all 16 lasers, you're going to get so many data points, it really clouds what you can see. Miguel, what do you guys normally set it to? 4? Pat? 4? Yeah, and trust me, I'm going to do another simulation where I was over in England with this and set it up on one of the little remote boats, and we were collecting multi-beam and LiDAR simultaneously along a bank line. So you're going to, and we were only doing 4 channels when we did that, and you're going to see the resolution that you'll get out of just 4 channels. But if I wanted to, I could click this to say check none, and we put the beam number, or the beam number, and we also put the degree that it is off the horizon. So if I choose just the inner 4, I'm going to choose 1, 3, 12, and 14, and hit apply. And now when I come over here, now I'm only looking at the inner 4 channels. And I know in just this simple setup, it doesn't look like a whole lot, but when you're moving along at 3, 4, 5 knots, believe me, they space and show you everything you need to see. But so this is just how simple it sets up, interfaces with Hypack. And of all the LiDARs that I've worked with, it is simply the easiest to interface with Hypack. Several of the more expensive systems, and what's really odd is you go from this model at $5,000, the next model up is $50,000. But we're talking about going from a 3 millirad beam divergence, so again, 1 foot diameter red dot at 300 feet. The $50,000 system is a 0.3 millirad dot. So at 100 or 100 meters away, it's 3 inches in diameter. So it's a much finer point. That's why you're paying for a more expensive laser. And it also can go out anywhere from 150 to 250 meters. So it has a much longer range that it can reach. So again, you pick the tool out of your toolbox that's going to do the job that you need to do. So this may not do everything you need to do because it doesn't have the highest resolution, doesn't have the longest distance. You may need another laser, the $50,000 laser or the $150,000 laser that can reach out 1,000 meters. Right? So it just depends on what you need to do the job that you're required to do. But this is just how simple it works here. Also with the Velodyne controller, not only can we change the range or the distance, we can change the field of view angle. Right? So in this, I could tell it to, what you want to tell it, and this is the little thing about this filter, is you actually tell it what you want to keep. All right? So if I say I want to keep from 30 degrees above, so in this case, on the Velodyne, the cable coming out is at 180. So 0 is the opposite side. So if I said I wanted to keep from 60 degrees out here to 300 degrees out here, I've clipped out this 120 degree area. So I would tell it I want a minimum 60 to a max 300. So 60 to 300, I'll hit apply and tell it to. So now you can see that I've clipped out this wedge right here, and that data is not coming in. I could set it to 90 and 270, and now that would just do straight out and everything below it. So we've created these nice little controllers for most of the lasers where you can do things like this. And in the editor, there is a way to also, if you wanted to collect all 16 beams, we have a filter that we can use that can trim them out. Yes? So if you're doing a beam on one side of the boat, you could. So if you were just doing this right side over here, and maybe you know there is a bridge coming up, and you want to make sure that you capture the underneath of the bridge, then you might want to leave it from 0 down to 180. or 0 down to 120, something of that nature. Yeah, it's all simple settings that you'll just become familiar with if you get a system. And this also will be used, so if we were collecting multi-beam and LiDAR simultaneously, the real-time cloud window will be showing you both. It also paints the matrix with both. So you'll be able to see how far you're reaching up on the bank with the matrix as well. All right. So that's how simple it interfaces with your computer, talks to Hypack, sets up with a mounting bracket. Anybody wants to take pictures of this or have me send them, just send me an email to joe@hypack.com. I've got plenty of pictures of this. It's a real simple 4-inch aluminum channel with a 3/8 plate and a 3/8 plate here. And you have, if you've got a good welder around, just have them weld this all together. Then you can just drill your holes and put your pins in. I've got a handy little machine shop 4 hours from here that builds these for me, and I ship them around to people. They charge somewhere around $150 to $200 to build that. But it depends on, I wouldn't build it too much taller than this, because now if you try to do something up around here, there's a potential for this to vibrate and wobble while you're going along. So you want to build this, again, just like a multi-beam, as rigid as possible so that there's no movement. And again, it requires RTK either in real time or post-process, because this will show movement if you don't have that positioning. The first time I hooked this up, I was just doing some testing and I didn't have RTK and I just had DGPS. Went out to do a patch test and I couldn't figure out why. I just couldn't get everything to line up. I could tell it was a horizontal shift. I finally figured out it was the differential positioning that wasn't bringing everything as tight together as it needed to be. So I've got a project that I collected over in England on, if anybody's seen the Hypack boat that's over there, there's 2 of them. One's in the Sontec booth, and then I forget where the other one is. But anyway, the other one has a LiDAR system on it. I actually should have a little video on here that I might be able to play as well. Groups. There we go. And make sure this is still set up. Good. All right. So here we've got multi-beam running simultaneously, and here's the real-time cloud. I'll just make it full screen. We can see it's reaching both sides of the bank with the LiDAR. Here's the multi-beam being collected below it simultaneously. They did not have a tilt bracket on the multi-beam, otherwise it would have been shooting all the way up to the key wall that's over here. And they're going to be steering the boat over here towards the key wall here real quick. But you can see it's picking up the bank lines, it's picking up this building way up here on top of the bank. And again, this is 4 channels of the 16 running right now. There's a person walking along the top of the key wall right there. And this was a class that I did over there, and 3 of the guys knew that what I was doing. Unfortunately, there wasn't a 4th, and what you're going to see up here on the wall here shortly is they were doing the YMCA. So you got one guy going like this, you got another guy going like this, and another one doing this, and they didn't have enough to do the A, so that'll be coming up here in just a second. All the yellow is, that's picking up the water, the foam on top of the water. Again, it's picking up stuff in the water, yeah. So your aeration from so you can see there's a person that was walking along, so it started picking them up, and finally they stopped walking. But you can see the light standards up here on top of this other wall. Now there's a flat surface right here, so you can see just the resolution that 4 beams picks up along that boat that's sitting there that's moored. There's one guy. You can see the ladder coming up off the sidewall there. This is tilted 45 degrees, yeah. No, the multi-beam is not tilted. They didn't have a bracket for the little remote boat that they were running. If we had Chip, then you would have seen the 90-degree corner down here and coming up to the bottom of the water line. But you can see the laser is good enough to pick up all the lines on the sailboat here. So there's somebody doing this over here. Oh, yeah, there it is. And so that guy thought he'd... Yeah, so I did a demonstration in New Orleans before they bought theirs, and the next day they said, hey, we've got some engineers that would like to come see this. And the next morning there was a line of 15 engineers standing on the dock. And we did the demo for them. They bought one a week later. I came back to help them do the calibration and setup, and unfortunately, a towboat sank, and we got called off, and we had to go down and do the survey of where the towboat sank, and it was right under a 600-foot container ship, and we had the laser still strapped on, so we collected both multi-beam and LiDAR, and what was really interesting is the anchor chain coming off the bow of the container ship, we were able to track it from the container ship and then see the continuation in the multi-beam all the way down to the anchor. But you can see 4 channels, just the resolution it's getting here on the boats. And so again, if you have to do regulation work for your regulatory branches, or you're doing INC charts or ENC charts, and you need to mark all the aids, and here comes the YMCA. You can use this to collect all that data and then just come back in the post-processing and pick up all of those as targets in the editor. So there you go. Now, Rocky statue, no, that's the guy doing the Y and then the M and then the C. But typically, you're just going to use this, on one of the passes that you're collecting data. The pass typically closest to the bank line, you're going to use this to collect the bank line stuff, and then literally you'll just turn the laser off and then collect the rest of your multi-beam. So you'll only have a couple files that'll have the laser in it if that's what you're trying to do. No, it stores it in the same HSX file. It stores it as a TOP record for topographic instead of an RMB record, which is a raw multi-beam record. But it still will use all the same position, motion, heading data that you're providing for both systems. Is there a way, let's say, when you were doing the post-processing, you only wanted to look at the LiDAR data? Yes. So you can only look at one or the other at a time. But if you want to look at both in the editor, there is a simple little trick to do. No, that's one way, but the simplest way is to actually open up the editor, choose the multi-beam first, just get it into stage 2. You don't have to do any editing to it, and just simply save it out to the HS2X format that Mike talked about yesterday. Then reopen up all the HSX files, except this time choose the LiDAR instead of the multi-beam in the editor, and get it to stage 2 and immediately save it to HS2X. And he's written the program so that when you process LiDAR data, it puts a underscore topo in the prefix of the name. So it'll have the same first HSX part, but there'll be an underscore topo HS2X. Then you can load all of the HS2X files together, the underscore topos and the multi-beams, and be able to see all of it at one time. So again, if you have a need for something like this where you need to do bank line surveys just to continue on from what you've collected multi-beam, again, aids to navigation, anything for your charting, bridge clearances, anything of that nature, then this is a very handy tool to have in your toolbox. And again, also, this is just 4 channels running at one time. Of course, the boat's only running at about 2.5 knots right now. And again, maximum reach of about 100 meters. Typically, I would tell you no, just one pass. Again, what's going to happen is the data is going to be so saturated that it gets really hard to see features when you do both passes. And because it's so fine, if you don't have this literally measured to the millimeter, and even as accurate as RTK or even post-process data is, you're talking about 2 to 7 centimeters of accuracy for your positioning system. You're talking about this having about a 5 centimeter resolution on its positioning. So if you add those two together, now we're talking about a 10 centimeter resolution, which is going to be about 4 inches. And so, Donnie, if you collected in both passes, there's a potential for things to shift 2 or 3 tenths. And now things aren't as crisp as they were with just the single pass. Now, if you're worried about trying to get to bare earth, then a second pass in opposite direction may potentially get you more data to the earth, because you're going to take out all the vegetation and the trees and everything. So at that point, you're not too worried about it, and now you're getting more data points to the bare earth. So the multiple passes for doing something of that nature would be a benefit. But if you're trying to see corners of buildings and light poles, it's very possible that light poles can have just a slight shift in them and they're not as crisp as they were with just a single pass. And it's not like you're trying to measure a light pole to this type of accuracy, so the one pass should do what you need it to do. But again, if you're trying to do the bare earth, then, and just to give you an idea, I'm going to play this real quick. I got plenty of time left. If I've got the link still. If not, I can get to it real quick. I don't. All right. If you haven't seen this on National Geographic yet, I highly recommend that you watch it. It's called Treasures of the Mayan Snake Kings. And this is pretty amazing. Okay. So see the jungle that they've got here now? This is covering the area that the Mayans lived in Guatemala. And they're taking $1 million LiDAR system, putting it in a Cessna, and they're flying over, and they're mapping all of the structures that can't be seen through the jungle right now. And so you can see how thick the vegetation is here, and the LiDAR is able to get through that and get to the bare earth. But there's a 2-part series on this. They're both an hour long, and they estimated the Mayan, so you can see the terrain they're able to get So that's removing all of the jungle vegetation. And that's what they're able to see now with the LiDAR data. So, I'm sorry? Treasures of the Mayan snake kings. So they originally estimated the total Mayan population at 2 million people. They're now estimating it at 20 million people with the 60,000 plus features and buildings and everything that they're able to see now. And they've only mapped 1/5 of the jungle so far. But I like to show this because it just shows you what the LiDAR can give to you. Again, that laser is just spinning 360 degrees, so it's called, Pradeep, help me, what's it called for it's direct return? There's a phrase that it's called for the LiDAR. Anyway, so the light ray, if it gets by everything through a nice little hole between all the vegetation, hits the ground and comes right back. Remember, light travels at 186,000 miles a second. So, it does it very fast. It does get between things and get back. But you can see it's not as crisp as you would expect it to be because it's not getting complete coverage on the objects. But the objects that are out in the exposed area do have better detail. But you can see the roadways that are covered up by the vegetation. And, they're going to show you that there's this pyramid that they didn't even know existed that's just a couple hundred yards away, but the vegetation is so thick on it. And you can see it's coming up right there. But if you watch the whole thing, they're finding pyramids that are like fire towers in our forests that are on peaks far away that they literally use smoke signals and smoke fire and fires to send signals and communicate with other Mayan villages. Yeah. So I don't think it shows anymore here, but again, I highly recommend that if you get a chance to look at it, it's a 2-part series, and they go into great detail of what the LiDAR was able to show. All right, so connecting it's very simple, mounting it's very simple, setting it up in Hypack is very simple. Now, just like a multi-beam, and I know Mike's going to cover the patch and performance tests for a multi-beam, we also have to do a performance or a patch test for the laser. And it's a little bit different than the way a patch test for a multi-beam works because a multi-beam is going over top of an object that's on the bottom. And the fan goes straight down. I'll stay right here, Rob. I'm just going to stay in this area. But so the fan is going straight down, and what we're looking for in a patch test is a flat floor to do the roll test on and some type of significant slope on the bottom to do your yaw, pitch, and latency tests on. So we need to do the same type of thing for a LiDAR system, but because we're not over top, we're on what we consider a non-aerial LiDAR setup. We're on a boat or a truck, and we're typically going out to the side. We need to now take what would normally be below us and look at something that has a right angle coming up from the ground and kind of look at it from that perspective. So because we don't go over top of it, I can't get over top of it if this was a tree or something. My LiDAR's not up here, it's down here hitting it from this side. So there's a little bit different way we have to collect the patch test data for a LiDAR system and a little bit different way that we have to do the processing. And it's more of the manual nature than it is of an automatic nature. So because if I've got this tall cylindrical object here, What we're going to do is we're going to create a box pattern around this where I collect the file this way, and then that way, and then back this way, and then back this way. And what I'm going to see is 4 halves of this cylindrical object. Because in one pass I'm going to get this half, the next pass I'm going to get this half, which half of this overlapped on half of the previous one. The next pass I get another half-half overlap, and the next pass I get another half-half overlap. And with that, I'll be able to do my patch test. So I actually have a patch test here. And this is a non-aerial, so this is called the non-aerial non-aerial LiDAR patch test. And if you go to our website, where's my link? And if you just type in, let's just type in aerial, do a search. There's 32 articles, and first one, performing a non-aerial LiDAR patch test. And it's using this exact project that I'm getting ready to show you. And it walks you through all the steps of doing a patch test. Now, just to give you some ideas, there's more than one way that we can set up a LiDAR system. And so here I am up in Grand Haven, Detroit. Trying to think of where these guys are. Yeah, Grand Haven. Okay. And I took this setup right here, and this was before I had the aluminum bracket built. I went to Lowe's and bought a simple L bracket, bent it 45 degrees, 2x4, and bolted it to the top of the boat. I mean, that's how simple that bracket was. Right? This is the very first one that I built that's strapped on top of my truck. I live in Panama City, just 4.5 hours to the west of here. The Panama City site office for the Corps of Engineers, I work with these guys all the time. And I knew they had just upgraded to a POS MV, and I knew they had a Trimble SPS 461 dual antenna system sitting on the shelf doing nothing. I knew they had a TSS DMS 05 sitting on the shelf doing nothing. And I said, hey, if you'll let me borrow this for about a month, I'm going to show you something really neat. So they let me borrow it. I went and bought this 8-foot piece of 4-inch aluminum channel, and much to the dismay of my wife, in my dining room, I put a big blanket over our dining room table, and over a matter of about 2 weeks built this system. And went back and showed them what it could do, because they had a project where they were doing beach surveys, and they had to do 28 miles of the Fort Walton Beach. And they had done a study to figure out it was going to take them 3 months to do the normal backpack 100-foot cross sections all the way to the dunes of this survey. And when I asked them to borrow this stuff, I said, yeah, I can probably do that in 3 days. And they said, there's no way. I said, all right, well, let me borrow this stuff and I'll show you. And so went back a month later and had this set up and said, yeah, so, you know, with something like a beach survey, 10 minutes after you go by on the beach, 1,000 people have walked by and completely changed the terrain anyways. So you just want to get the one pass across it. And because this thing can reach 100 meters, it's 100 meters to both sides. So that's really a 200-meter swath. Right? So now we're talking about 650 feet that it's covering. So literally I could almost do in one pass from the water line to the dunes. And even if I did 2 passes, I would for sure get it and have overlap in the middle. And the other thing to understand about LiDAR is the color of the object that it reflects off of makes a difference on how well it reflects. White is the best reflector for LiDAR, black is the worst. Same way it works for the sun. You know, if you had a black car here in Florida year-round, you want to keep it in a garage because the black absorbs the heat from the sun. Most people here have white cars because it reflects the heat from the sun. Same thing with the way the LiDAR works. The white reflects it back very good. The black absorbs it. So also, sunlight is a great reflector of the LiDAR. It will pick up the sun's reflection off the water. Right? So they prefer, if you're going to use LiDAR for terrestrial type work, do it at night, because now there's no sunlight that's affecting anything, and that does cause issues with the LiDAR getting its reflections. So if you collect at night when there's nobody on the beach, then in a matter of several hours you could probably, so if you're running 5 miles an hour and you run a 28-mile stretch, you can run that in about 5 hours, 5.5. Right? 2 hours, if you did 2 passes, it's going to take you about 10 or 11 hours. So start at night when nobody's on the beach sunbathing, run down the beach in one direction, turn around, come back. By morning time, you're done. But if we wanted to do it in 3 separate days, 3 8-hour nights or something like that, you could do it. But like I said, this took a lot more wiring and everything. It's a much simpler if you've got an inertial system like the New York guys had a nice Coda Octopus F-180 sitting on a shelf doing nothing, and so they bought one of those Rangers, right? Is that what it is? A Ranger 4-wheeler. Built a nice bracket in the back end of it, and these guys are doing beach renourishment surveys and all kinds of land topo work with it. But this is just, I call this the old school cheap way to do it. If you've got these pieces of equipment sitting on a shelf doing nothing, for $5,000 more, you can put one of these rail systems together.
Are these systems recording density values?
Yes.
You guys are picking all that up too?
Yes. So after I built that poor man's version of the LiDAR system for the Panama City Corps, they went ahead and bought the additional SBG Ellipse 2D, which is the small inertial system that you'll see out here at the SBG booth. And we built this so it's a lot more compact, it's a lot lighter weight, a lot less wires, and you've got the nice little IMU that's about the size of your cell phone, and it's all wired together in here. And we went out and did a test on the beach, and we set up 5-gallon buckets with bricks on top of them. They brought their backpack GPS. We took shots on it for check shots. We hit them within a couple hundredths with the laser. So we were doing a comparison on that. This is, if Matt in here, Matt Staley. Anyway, if you see Matt Staley from the Corps out of their headquarters office, after he started seeing this, he copied again the brainchild of the New York district and the backpack unit that they had, and this is the backpack unit that he built. And he went over and mapped all the graves from the Normandy battle in France. And he mapped all the headstones in the graveyards over there so that now they can make this nice 3D model and have all of them labeled, and you can click on any one, and it's something that they're putting together right now. So they walked all the graveyards with this backpack unit mapping the graveyard and the headstones. So anyway, again, we need to do a patch test for this setup. So this one here on the left is the one that I'm getting ready to show you, the project that I've got up. And it is a nice aid to navigation in the Falmouth Harbor in England. Nice conical concrete shape with nice vertical here, the 2 little balls on the top. Question? Okay. This is when I went out to Missouri and the USGS and built a rail system for them, and this is the light pole that we used to do the calibration on, and it worked out really well. So this is, again, online on our website if you want to follow step by step. Typically, the one thing you're going to see the difference in on the patch test is with the multi-beam, when you do the processing, there is a specific order that we do the processing, and it's latency, roll, pitch, yaw. With a LiDAR, it's the opposite order. Latency is always still first, but angularly it goes yaw, roll, pitch, because you have to get the yaw lined up, because remember, we've got 4 semicircle halves of this cylindrical object, and if I don't get those lined up in some close fashion first, there's no way I can do the roll and pitch offsets. So we have to do the yaw first to get this object oriented correctly, and then we can do the roll and pitch offsets. So this is what it looks like from the side. This is what it looks like from an aerial. So again, this is what we're going to see. These were the first passes that we made. So I'll just close this part right now, and we'll go actually into the test. All right, so we'll just select all 4 of these. So Mike, get back to your question about, can we edit simultaneously? When we get to the Devices tab here, under this edit, we choose whether we're going to do the multi-beam as the sonar or the LiDAR as the sonar. So this is actually the Renishaw Merlin, or the Carlson Merlin now, that we were using to collect this data with. So this is a single point rotating LiDAR that was also at a 45-degree angle when we collected it. It has a really nice rotating tiltable bracket that it comes with. And what's really nice is inside their manual, they've got a chart set up that tells you from the pivot point of their bracket, depending on what orientation you have it spun and what tilt you have it at, it tells you the starboard, forward, and vertical offsets from that pivot point. It's a nice little chart that they put together. So again, we go ahead and we put in the tilt that we think it is. So this has already a negative 45-degree pitch put into it. And the other key thing, remember I said you have to have RTK. So we're going to use RTK as our heave device here. Because you can't apply the normal heave that you would do to a multi-beam to a LiDAR system. You just use the RTK. All right. The other thing Mike explained to you yesterday about in the editor is we want to make sure that we're applying the grid convergence, because our lines of longitude, they merge together as you go more north and south.
It sinks so fast. I love it.
Wow. Okay. Sure. Yeah. So under the sonar button, under the processing tab, there is the apply grid convergence. And again, as Mike explained yesterday, because of the way the lines of longitude merge together towards the north and south pole, the more you move north and south, the more the convergent affects the yaw offset. And the more you move east and west within it, affects the yaw as well. And we had one of our users over in the UK who had purchased a LiDAR system, and he was finding that every time he moved 50 miles north or south, of course, UK's at a higher latitude than we are, his yaw offset was changing by a ½ degree. He kept wondering why he had to do a patch test every 50 miles with the LiDAR system. And it was because of the grid convergence. So now if you apply this grid convergence to your patch test, then that's already factored into the yaw offset that you have for your patch test. And any future data you collect with your LiDAR system, as long as you check this box, it will properly apply the correct grid convergence, and you don't need to redo a patch test. All right, so we'll load all the data in, and we can see the 4 passes that we made here. It's just a simple box pattern in a northeast, southwest orientation around your object, which is going to be here in the center. All right, so we can look at the speed. Speed looks fine. And let's look at there's our tide. So this is the RTK we're going to use, the yellow line. We're not doing heave. So this is what's going to be compensating for our vertical up and down that the boat experienced. All right, heading, pitch, and roll, that's just simply what was being measured by that device. And sound velocity has no effect here in LiDAR data. So we can just take this to stage 2. And I've got a very fine resolution. So remember, this is a meters project. My grid resolution for my matrix is 5 centimeters, right? Because that's how fine the laser is. So I'm going to zoom in. We can see that there is some kind of a yaw misalignment right now between this. So I'm coloring by elevation right now, but if I, color by, that's right. So in this window, we're coloring by elevation, but what I'm going to do is use this little cloud pop-up window, and I'm going to zoom in around here. And now it's coloring by file. So I can see the misalignment yaw-wise between my 4 halves of that object out there in the middle. So this is where the patch test for, and this is the best I've been able to figure out so far for LiDAR systems, is it's all manual. Because there's no way to cut a cross-section to line things up because I'm not over top of it. I'm hitting things from the side. And because I hit things from the side, if I just look at, say, the red and blue files, which are going to be the files 1 and 3, then I really have nothing that overlaps because I need to cut the cross-section right here in the middle. And I don't have anything that overlaps. I have 2 halves that I'm trying to slide together. So I have to manually guess what value to use to bring these together. So I can just look at the 2 halves that are running like this. I can look at all 4. It doesn't matter. Sometimes just looking at 2 makes it a little easier. So I see, I like, because I can see that little pole. So if I look at 2 and 4, I can see the halves of that pole that's on top of this conical concrete base. So I'm going to look at 2 and 4. So I'm just going to take 2 and 4 into stage 2 so that I'm looking at just those 2. And what I'm going to do is I'm going to open up the read parameters window. I'm going to go to the devices tab. I'm going to click on the patch test and I'm going to say, okay, I'm not really sure if it's a plus or minus, but let me apply a 2-degree positive yaw, and let's see, do they slide further apart or slide closer together? So I at least know whether I'm on the positive side or the negative side of it, right? So I'll say, okay, update. I went too far. So it's on the positive side, it looks like, because before the yellow was this side and the green, so let me cut that 1 degree in half. Let me cut this down to 1 degree. Okay, update. Okay, 1 degree gets me pretty close on the yaw. So if I want to zoom in here, I can kind of see this is the half of the green and this is the half of the yellow. So let me see if I can slide that a little bit better together. It looks like it's going to be a little less than 1 degree. So again, read parameters. Let's try 8/10. That's probably too much, but okay, okay. Update. Yeah, it's a little too much. So, and what you're going to do is you're just going to go back and forth till you get a pretty good alignment on this. And then we'll switch over to the pitch and roll. All right, that looks, so if I zoom back out, that doesn't look too bad. All right, 9/10 of a degree for the yaw. All right, if I want, I can go ahead and just bring in all the files. And that doesn't look too bad right now, making this line up. And if I want, in this, I can kind of tilt this and look at it. All right, that's looking pretty much like the object that's out there. There's still some pitch and roll that needs to be done. There's still slight misalignment here. You see the yellow's a little bit more there. But you can see how that 45 degree is giving me this candy striping going down the object and giving me the full semicircle around it. where if it's cutting it vertically, I may not see the full tangents of something that's more straight up and down. This being conical, it would probably, I'd have candy stripes, or I'd have stripes just coming vertically up and down and wouldn't be seeing a nice edge of that conical shape. If the LiDAR was on a drone, I would do it exactly the same way I do a multi-beam, because I'm now over top. That's why I've named this the non-aerial LiDAR patch test. So I'm pretty close here, so now I need to work with some pitch and roll. So now I need to kind of know which lines are running which direction. So I'm going to go ahead and close this window. And if I zoom in here now, I can see that that's looking a whole lot better. But I probably want to trim some data out that I've got some bad points, so I'm going to turn this, in this view, I can turn it this way. And I'm going to zoom in, and I can see that my max height on top of those objects, those two balls that are on top of, I'm going to catch myself before I say it again because I always do this. The two balls on top of, I just don't have a good word to say now. Spire, there you go. So the top height there is at 15, a positive 15, and down here at the water line, we're at a negative 2. All right, so I'm in elevations now. So I was in elevation mode when I loaded this data in, which means now everything is positive going up and negative going down. So when I do my filters, I have to remember which way is positive, which way is negative. So my minimum is going to be, let's see, going to be in the negative 2 here. Let's see if I get this wrong. And my maximum is going to be 15. Let's make it 16. Hit update filter preview, and that looks okay. All right, so I'll tell it to remove all the points that are outside of that, which is 539. I'm going to tell it to update. Now my colors look a lot better. So now when I look at this straight down, I don't need to show the deleted points. And zoom in, my object's looking pretty good there. But what I need to see is which lines run parallel to each other. So 1 and 3 run parallel to each other. So I can try to use those to do a pitch, or 2 and 4, either way. So I'm going to choose 2 and 4, and just take those two into the patch test. And again, I'm going to take my little cloud window and zoom in around this area. And so you can tell the green ran across the top and the yellow ran across the bottom. And if I cut it this way, that's going to be a roll test. So if I take this, and let me turn it around 90 degrees this way. If I were to cut a cross-section across the middle of this, that would be my roll test. But I'm going to turn it so I can see it this way. And the other thing that you have to remember, too, about seeing things from the side is I see this half and I see this half. All right? What the patch test is going to try to do is make lines line up. So it's going to try to take this outer edge and make them line up like this. You now have to visually understand that you're trying to bring it together like this. So when I zoom in, what's really nice to know is if I know the diameter of the object that I'm doing the survey around, I can easily use that as a check to know if I've got it sized correctly when I start adjusting the angles. If I had a really bad pitch or roll here, I would see those two spires sticking up like this at an angle or in a V pattern like this. They're already really close, so I'm not going to have too much of an adjustment to make to pull these apart. So again, it's the same procedure. We would go up to the read parameters window, we'll go to devices, and I'm looking at a roll right now, so I go edit, and I don't think it's going to be very much, so maybe I try like 0.2 of a degree. You know, okay, okay, and update, and that pulled them apart. And again, if I turn it to look at it from this perspective, if I knew the diameter of this, I could measure across what I think is the diameter part and get this to line up a lot better. But it's looking pretty good right now. Again, if I knew the diameter of these two balls that are on top here, right now it's showing that they're 55 centimeters. All right? If I knew that they were 50 centimeters, I know I only need a minor adjustment now to try to get to that 50 centimeters. So I'm going to leave it at this 0.2 degrees right now for roll. And again, if I look down at the top, pitch now runs this way. And if I spin it back around, I can use these same two files. And now if I turn it sideways, I can see that there's a slight misalignment between the balls up here. And again, it's probably going to be a very small amount. And I'm going to go back into the devices, edit. I'm going to adjust the pitch. So it's at minus 45. I'm going to say minus 44.8. I'm just going to try 0.2 on it. Okay, okay, update. I think I went the wrong way. So I think it's going to be, that type of, let's see, I can't remember, I'm not sure what I changed there. Okay, minus 44.8. So I think it should be maybe minus 45.2. Right, okay, okay, update. That looks a lot better. So basically what I'm going to do is I'm going to go through the yaw, the pitch, and the roll again and try to get this object to be as best aligned as possible. And then again, if I go ahead and bring all the files together, I get something that looks like this, and let's turn it sideways, and that doesn't look too bad. All my sides look pretty good. You know, I'm spinning it around, seeing if I see any misalignment on the slopes here. And that all looks pretty good. I mean, I would probably try to fine tune it by a couple more hundredths on all the degrees for the yaw, pitch, and roll. And once I get that in a good, happy spot, then I'm pretty much thinking I'm done for the patch test. I'm going to record these values, update my hardware setup with these values, and now I'm ready to go survey. Yes, Katie?
Can you explain again how to choose? Did you say you look at it from the plan view to choose roll or pitch?
Yeah. So
Rotate it a certain way for each?
right. So with the so if we just turn on, say, two that run opposite directions of each other. So we know that the blue ran across the top here, and the red ran like this. All right. So they're opposite directions. So when you cut the patch test for roll, you cut it perpendicular to the run lines, which that would be a north-south cut here. And for pitch, I would cut it in parallel to that. And basically what I'm visually doing this. I cannot cut a cross-section on this because all I have is two tangent halves. They don't overlap. They just touch each other. Right? So if I tried to cut a cross-section right through here, I'm not going to have hardly any data points that overlap one another, which is the difference between a non-aerial LiDAR and a normal aerial LiDAR or multi-beam patch test, because you go over top of the object, and now you can cut cross-sections because you have like points that overlap one another.
So when you do the roll on this one,
So if I do the roll on this one, what I'm going to do is I'm going to rotate this around like this, because I know I want to look at it in the perspective of cutting it this way. So what I do is I just get the two halves kind of lined up in a north-south orientation like this, and I click on the profile view. So that now I see it from the side, and what I'm expecting to see is either a V pattern or a cross like this. And I'm going to start adjusting the roll values till I get them to be parallel. And now you can see how I'm seeing the outer half and outer half of these two passes. And if I know the diameter, and this is how we did the patch test with that light pole with the USGS, is we were actually on the ground, and they went over and measured the concrete base, and they measured the pole, and we would come over here, and we would measure from outside to outside, and now I'm at 0.25 meters, all right, for the horizontal distance, and that's probably about right. That pole is probably about 25 centimeters in diameter, right? And again, if I knew the diameter of the two spheres on the top, they're right at a half a meter now. These values sound pretty logical values to be something that's man-made built for this to be. But if I had the true measurements, I would use them to guide me to adjusting the angular values. All right. So again, I could bring in all four. And there's a little cross that goes down across this as well. But like I said, I'm going to look at this from top view, side views. I'm going to spin it around and be able to look at the adjustment for the angles. Once we've got it, now I can record it, and if I go in here, I can see just how well it looks. And I'm going to go back to this. So I show you all the steps that I ran through on this particular project, how the four halves didn't line up, and how we can look at the different colors, start sliding things together, and get our end product. And this walks you through all of it. Katie, if you want to look at this article. Yeah, so you can see the two halves there, and how I'm trying to get them to line up.
Joe, this is on a boat.
Uh-huh.
You put the sensors on the boat, and it's not set up the way you have the truck with the rail.
Right.
Where everything, where that's
Yeah, so with the rail is eventually the vessel and the equipment. So once it's calibrated, it's a complete plug and play, put it on anything.
at any angle.
Should work, yep. The only thing you may have to adjust, and this is one thing that I did find out from the guys at SBG, is, now this is just the SBG, I'd want to talk to, is John Cars? John, okay. About the way the methods work. So with an SBG, they have aerial, marine, land type settings. And John, you'll have to help me with the way, if the pause has anything similar to this. And the reason I'm mentioning this is with the SBG, if you say you're on a land vehicle, they're expecting that it can't drift side to side. So with the land, what they tell you to do, and it was kind of surprising when I found this out, is for the center of gravity, it's the rear end of your rear axle. Because that's literally the pivot point of that vehicle. Because it can't slide side to side, and the rotation is pretty much right there at the rear end of your axle. So you measure from there as your COG up to wherever your rail's mounted. And that becomes now the pivot point for the system. Now that's the way the SBG works. I'll talk with John to see what might be the best recommendation for doing the same thing in the pause. Right. Okay. So the best thing, we'll just talk to John about maybe the best way to do that for the pause. Right, it's all an all-in-one. But again, what you're talking about is however you mount that. You know, if you mounted it on something like this, we need to know where it needs to do the pivoting from. Yeah, I understand. Yeah, trying to do it as level as possible is the best orientation. Then, you know, as the vessel moves around, they should move all together. Yeah. Yes, for all the angles, it's perfectly good. What may be different is the way it does height changes based on the angle of the mounting system. But if it's pretty much parallel to the vessel, then I wouldn't expect that you need to change it too much. But like John's saying, the way the Kalman filtering works for the positioning with a land-based vehicle, we know there's no potential to slide sideways because it's going to track with the truck or boat or whatever. But on a marine vessel, the Kalman filtering works a little bit different because it's expecting there to be some of this while it's doing its positioning. But so when we were finished doing the patch test, I just brought these two images together to show this is what it looks like in the real world, and on the left-hand side, this is what the laser data looked like when we were done with it. And they were really pleased with it. All right, 3 minutes over again, Rob. Oh, yeah. If anybody's got some other questions, I'm handy for it. Is it 5? Okay. For all the Corps of Engineers personnel that's in the room right now, we're going to have a Corps of Engineers meeting with you guys at 5 o'clock if you'd like to attend. As we know, the room will put something at the registration desk. Oh, yep. Okay, and where does it say where? Oh.
The other thing is the Norbit demonstration. I forgot to mention that yesterday. So if you want to see Norbit demo this system, just check it for your visitors.
Yeah, if it's going to be at the boat dock that I'm thinking of, Pogo, is he still here? Pogo. So if we go right out the front door here, and if you turn right about 600 feet down, there's a low water dock that's right under the blue bridge. I'm assuming that's probably where it's going to be, but the guys at the Norbit booth will be able to tell you for sure. But I know that there's a low water.
There's like a river taxi thing down there.
Right. Yes, but if you head out and head towards the blue bridge, there's a docking facility right there. But check at the Norbit booth for sure to make sure that's where they're going to be. All right. Any questions? If not, thank you for attending, and we'll see you at the next session.